Hello and welcome to this video. In a simulation, it is common that we need to analyze large assemblies with many different parts. In finite element analysis, even if two independent parts are touching each other without any gaps, the two parts do not see each other. In other words, the relationship or interactions between the different parts must be specified by the user and is not assumed by the program. If the interactions are not defined correctly, the simulation results can be misleading or wrong. However, for large assemblies that may have hundreds of parts, creating connections manually can be very tedious and time-consuming work. So, is there a better way to connect the different parts? In Ansys, we have two options to define interactions between the neighboring parts. The first option is to use shared topology, and the other option is to define contacts. In this video, let us learn how to use these two options in our analysis. Let's go! We already know why we need to connect different parts of an assembly. Now let us learn how to connect them. The first method is to use shared topology. In Ansys Discovery, we can use shared topology to connect different parts if the parts are to be treated as bonded or welded together. As the name implies, with shared topology, the interface between the two parts is shared. This means that in the FEA simulation of the assembly, we can have a single surface and a single set of nodes shared between the two parts. As a result, the mesh generated with shared topology is conformal between the adjacent parts. By conformal, we mean that we have a continuous mesh across the two parts. We need to remember that shared topology does not combine two geometry parts into one part. We can still have different materials on the different sides of the interfaces. What shared topology does is to tell the meshing algorithm that the two parts should share nodes at a common boundary, so the degrees of freedom are continuous. Ansys Discovery can automatically detect where shared topology can be applied on an assembly, and the user has control over excluding certain areas if needed. We will show you later in the demo part how to define shared topology. The second method we can use to connect different parts is via contact in Ansys Mechanical. There are different contact behaviors available, but for bonded or welded kind of behavior, we use the bonded contact option. Details on other contact behaviors are covered in a separate video. Here, we can think of bonded contact as a contact setting that glues or bonds different parts together in our simulation. Regarding the meshing of a model with contact, the two sides of the contact interfaces are meshed independently, so the degrees of freedom of the two parts are not continuous. Since different meshing and size controls can be utilized on the two parts, this provides user with flexibility in meshing the assembly. In Ansys Mechanical, we don't need to manually create contact between different parts. Ansys Mechanical can detect contact automatically. We can specify a tolerance to control the threshold of adjacent surfaces considered for contact. Even if the parts are not exactly touching each other, the solver can treat them as bonded together. Given these two methods, shared topology and contacts, how should we choose the right one for our simulation? First of all, simulations using shared topology or bonded contact should result in the same behavior. However, each method has its pros and cons. Bonded contact allows for each part in contact to be meshed independently. We can have a coarser mesh on the parts that are not of interest while specifying a finer mesh for more critical components. This can lead to a computationally efficient mesh since we can invest elements only on the parts of interest. Despite this advantage, using contact may lead to some discontinuity or noise at the contact regions. On the other hand, shared topology does not suffer from this issue. Deformation results are continuous over the interfaces as the degrees of freedom are shared. The downside of having a continuous mesh is that it may increase the complexity of obtaining a good quality mesh, especially when transitioning from a finer mesh on small parts to a coarser mesh on adjacent bodies. A side note is that if the parts are expected to separate or slide from each other, shared topology is not appropriate. Because the degrees of freedom are continuous for shared topology, any relative movement between the parts is not allowed. For such situations, we must use contact. As mentioned before, besides bonded contact, there are other contact behaviors such as no separation, frictional, frictionless contact that we can utilize to allow separation or sliding between touching parts. Now, let us use a simple example of wall bracket geometry to understand these two methods. We have divided the bracket into two parts, top and bottom. There is a bearing between two brackets and the bracket is mounted on the wall. For demonstration purposes, we are not going to model bolt connections and we will assume that all parts are bonded or glued to each other. We will define the interactions between the components of this model using two methods, one with shared topology and the second with contacts. To start with, let us insert a static structural analysis system into a fresh Workbench project schematic page. Then go to the geometry cell and right mouse click to insert geometry. Browse to the bracket_1 file and select it. Now double click on the geometry cell to open this geometry in Discovery. In Discovery, we can see that there are different components for each body. We can go to the Prepare ribbon and access different options related to shared topology. We can share or unshare the topology between neighboring bodies. There is an option to review shared topology results. Now let us perform shared topology for this model. Note that only visible bodies are searched for sharing candidates and hidden bodies are ignored. Once we hit share, it will identify the sharing candidates based on the coincidence tolerance. If there are tiny gaps between the bodies, we can increase the coincidence tolerance accordingly to increase the range of detection. For example, there is a gap of 0.15 mm between the bearing and the brackets. So if we keep the coincidence tolerance at 0.1 mm, then it will not detect those candidates. So let us use coincidence tolerance of 0.2 mm for our case. We can see that there are 5 faces and 37 edges identified for shared topology. Let us try to visualize the shared topology for this model. First, click on Review from the ribbon and then select the body to see all the relevant shared topology results for it. By clicking on faces, we can show or hide the shared and not shared faces of that body. We can also change the display color for the shared and not shared faces. Similarly, we can see the edges which are shared twice, thrice or more than 3 times and change their display color and line thickness. Clicking in the region outside the model will deselect all the selected bodies and show the shared topology results for the entire model. As we discussed earlier, during the shared topology operation, it imprints the faces at the common interface and merges them into one. Let us hide the bracket bottom body. We can see that it has imprinted the common face on the wall body. This imprinted face is shared between both the bodies bracket bottom and wall. Thus, when we mesh this model, it will create a common mesh and the nodes at this interface will be shared between these two neighboring bodies. Right-click on the empty space and show all bodies. Let us click Ctrl S to save the model and go to the Workbench project page. Double-click on the model cell to open Mechanical interface. In Mechanical Tree Outline, we can see that all the bodies are now part of a single multi-body part. If not set already, go to the Display tab and set the edge color by connection. This will show the shared edges in magenta color as we saw in SpaceClaim. Right-click on the bracket bottom body and hide it. Then select the common face that it has with the wall body. Now go to the Home tab and click on Selection Information. We can see here that this face is shared between two bodies, namely bracket bottom and wall. Switch off Selection Information and right-click in the empty space to show all bodies. Now go to Mesh and set Global Element Size of 10 mm. Set the selection filter to Body and select the bearing body. Right-click and insert sizing. Set element size of 5 mm for this body. Now generate mesh. Let us zoom in to see the mesh connectivity. If we switch to node selection, we can observe that these nodes are shared between two bodies. Thus, we have a conformal mesh between the bodies sharing topology. Switch to face selection mode. Let us set boundary conditions and loading for this model. We will apply fixed support to the end face of the wall body. Then select the inner face of the bearing body, right-click and insert force. Choose Defined by Components and set -100 newtons in z direction for downward force. Under Solution, let us insert total deformation and equivalent stress for this setup. Let us solve the case and observe the results. Go to the Result tab and switch on Probe. If we observe the equivalent stress more closely, we can see that the result averaging is not done at the common interface, even if they are shared. This is by design, as even with nodal averaging, we don't want to average stresses across different bodies. Now let us use the second method of contacts for this model. For this, go to the Workbench project page and insert another static structural analysis system. For better understanding, let us rename the first system as Shared Topology and the second system as Contacts. Right-click on the geometry cell in the second system and insert geometry. Browse to the bracket 2scdoc file. For this model, we don't have to do anything in SpaceClaim. Hence, double-click on the model cell to directly open it in Mechanical. In Mechanical Tree Outline, we can observe that all the bodies are separate, unlike the first case where they were grouped under a single multi-body part. As there is no sharing topology, it does not highlight any edges with magenta color when we set the edge color by connection. We can see that it has created the automatic contacts under connections. We can control the automatic contact generation using various settings. We have the option to choose the bodies for contact generation. We can also change the tolerance type and define the tolerance value for automatic contact generation. By default, it generates bonded contacts using this option. As the contacts are generated automatically, it may generate additional contacts based on the topology and proximity of the bodies. So carefully verify all the contacts if they are defined as expected. As we select any contact, it highlights the contact pair bodies in the display along with the individual body views. This is very helpful in visualizing the contact pairs, especially in complex assemblies. There is a contact and target pair for each contact. The contact face is highlighted with red color and the target face is highlighted with blue color. Right-click on contacts and rename based on definition for better identification. We are all set with the contact definition. Let us set the global element size to 10 mm under mesh details and add local body sizing of 5 mm for the bearing body as discussed earlier. Then generate mesh. Let us zoom into the common bodies and observe the mesh connectivity. We can see that the mesh is not connected anymore between the connected bodies as seen in the case of shared topology. Let us set the same boundary conditions and loading as in the previous case and insert total deformation and equivalent stress for results. Solve the case and observe the results for both the methods. Here we have both the methods placed side by side. The left side is the shared topology method and the right side is using contacts. The total deformation results match well for both cases. When we check the equivalent stress results, we see that the contour scale is not the same. So let us use the same contour scale to compare results. First, copy the top value from the shared topology model. Then in contact model, click on the second value from the top and click on plus sign to add a value. And then paste the copied value from the other method. Similarly, copy the bottom value from the contact model and in the shared topology model, insert a value at the second from the bottom and paste the copied value from the other method. Then right-click on the contour scale of the shared topology model and go to Independent Bands and select Bottom. On the other hand, in the contact model, right-click on the contour scale, go to Independent Bands and select Top. With the same contour scale, we can observe the equivalent stress results also have visibly similar distribution for the bodies. However, zoom in at one of the connecting regions for both the methods and activate the probe feature under results display. We can see that there is a bit of noise in the stress values for the contact model at similar locations. A point to note here is that with shared topology, we have nodes exactly on the edges where the two parts touch. However, with contact, we don't always have a node right at the edge of the larger surface where both parts touch. So that is what we mean about not having DOF continuity. While having DOF continuity is not required to get accurate results, it is useful to know that if results at the contact interface are of interest, using a finer mesh at the contact region will improve the results. This concludes our demo. Let's summarize the key points that we can take from this video. The first important point to remember is why we need to connect different parts of an assembly together. Creating the interactions between the parts of the assembly is important to capture their correct behavior with respect to each other. The interactions between parts must be a user input and not an assumption made by the software, since Incorrectly defined interactions can result in wrong or misleading results. However, in the case of large assemblies involving many parts, creating these interactions manually can be a time-consuming task. The second important point to remember is that there are two common methods for connecting parts: shared topology and contacts. With the help of shared topology functionality available within Ansys, the parts will share nodes at the common interface. On the other hand, when using contacts available within Ansys Mechanical, the parts are connected with the contact region despite not sharing nodes. The next important point to remember is the scenarios where shared topology and contact should be used for connecting parts. If the parts of the assembly are mostly bonded or welded with each other, then using shared topology for connecting parts may be a preferred option, especially if you are interested in the interfaces. On the other hand, if one or more parts are not of interest but are present to provide an appropriate load path, contact gives us the flexibility meshing parts not of interest with a coarse mesh without dramatically increasing the number of nodes and elements. It is also worth remembering that if the parts may have the ability to separate or slide with respect to each other, then contact should be used for connecting parts. I hope this video will help you in selecting the appropriate method for connecting the parts in the assembly. Don't forget to visit courses.ansys.com to discover more useful courses.